Hello everyone, I'm Muhammad and today I'm going to talk about a stochastic minimum vertex cover problem. This is joint work with my advisor Mahsa at Northeastern and Zhiyang at University of Austin. So first let's talk about the stochastic graphs. A stochastic graph G star is a subgraph of a graph G containing each of its edges independently with probability PE. So here we have a graph G. Suppose that we set PEs for all edges equal to zero point 0.5. This is the graph G star that we're gonna get. We kind of have the distribution of the input, but we don't know the actual graph. These are a generalization of random graphs. For example, for Erdős-Rényi graphs, we can say that the graph G is a complete graph and all the probabilities P are equal to a number P between 0 and 1. So what's the problem that we're trying to solve here? We are given a stochastic graph, which means we are given G with probabilities PE on all the edges, and we can query each edge to see if it's realized in the actual graph. So you can see this model as being very useful whenever we have a stochastic graph. We want to compute some aspect of the graph by just querying some edges and then returning an output. And so our goal is generally to minimize the number of queries while we do so. For example, other problems that have been addressed using this model are uh, maximum matchings, all pairs shortest paths, and minimum spanning trees. So our goal here is to find the near optimal vertex cover with few non-adaptive queries on this stochastic graph. So I know that sounded a little bit complicated, so let's go with an example here. So here we have a base graph G, which we see on the left. We have a graph with probabilities written on the edges, which means that PE of that edge is equal to that number. Then on the right, we have the realized graph G star. And with the red nodes are a valid vertex cover of the graph G star. Our goal is to query some edges in G to see if they are included in G star and then report a valid vertex cover for the graph, which is as close to the minimum vertex cover as possible. So in other words, the goal is to pick a degree bounded subgraph Q of G that has a small approximation factor. We define the approximation factor as follows. On the bottom, we have the expected minimum vertex cover of G star, which is the optimal solution, the expected value of the optimal solution. And on the top, we have the expected minimum vertex cover of Q star union G minus Q. Why do we have that? First of all, for the graph Q, when we query some edges of it, we define Q star to be the realized edges in Q. So we know which edges in Q exist and which don't. So we just have to cover the edges in Q star. And for the edges that we don't query, we have to cover those edges. Why? Because even if one of them is realized and we don't cover it, then we don't have a valid vertex cover. So we should um, get the expected minimum vertex cover of Q star union G minus Q. So our goal is to find a Q such that this fraction is minimized, at least as much as possible. But there's a trade-off between the number of edges we query and the approximation ratio. For example, if we query all the edges, then the expected approximation ratio will be 1. But that's not a good algorithm. So there are two previous works on this problem. The first one, which was first studied, this problem was by Bloom, Behnajad, and Derakhshan, where they gave a two approximation ratio, and then later it was improved by Derakhshan, Druvasula, and Haqtalab, which they improved it to 1.5 plus epsilon approximation. Um, so in the second work, they provide also a lower bound for the number of queries needed to surpass 1.5 approximation in the presence of order of n correlated edges, which is related to RS graphs. Uh, I'm gonna talk about RS graphs later. So what's the motivating question that we had for this work? It was that uh, what's the number of edge queries we need to find a 1 plus epsilon approximation for stochastic minimum vertex cover? Our result is a simple algorithm for 1 plus epsilon approximation vertex cover with query complexity n times RSN, which I'm gonna define later. This is tight with respect to the lower bound of Derakhshan, Druvasula, and Haqtala. So let's talk about Russo-Semerdi graphs, or in short, RS graphs. Uh, so these are fascinating objects in combinatorics, which the definition is simple, but uh, the actual bounds on them are very wide currently, and improving them would be very challenging and problem which will lead to a lot of other results because there's a lot of lower bounds and upper bounds based on the density of these graphs. So an RS graph N, R, and T is a graph where the edge set as E can be decomposed to T edge disjoint induced matchings of size R. And we define RS and R to be the maximum T for which RS and R and T exist. So you can you can see that when you have a um, fixed size for matching, then the number of matchings can't increase more than a certain threshold. So we define RS and R to be the maximum T for which RS and R and T exist. Proving bounds based on density of RS graphs is common in dynamic algorithms, communication complexity, and streaming algorithms. Here is an example of an RS graph. Here n is equal to 12, R is equal to 4, and T is equal to 3. So what does this mean? It means that we have a graph with 12 vertices, and we have 4 matchings, which are colored with different colors, and each matching has 3 edges. So you can see that these matchings are also induced matchings. This means that if you take all the vertices that have an edge with red, then no other color for edges exists in that particular subgraph. So the 6 vertices on the right is the subgraph of the red matching, and you can see that there's no other edge in that subgraph other than the red edges. So what's our main result? Our main result is that for any epsilon between 0 and 1, we let T to be the maximum number of um, matchings of size C times n for an n vertex RS graph. Um, Then there exists an algorithm that queries a subgraph of size Tn divided by P and finds a vertex cover with the expected approximation ratio of 1 plus epsilon. P here is the minimum uh, PE among all the edges. Currently known bounds about density of RS graphs is that if you fix the size of the matching to be Cn, then the number of matchings is at least n to the power of 1 over log n. And so there's constructions for it, and it can be shown that the number of matchings can't exceed n divided by log to the power of uh, order of log 1 over c. So you can see that on one side you have nearly n, and on the other side you have n to the power of 1 over log n, which is really small, so there's a huge gap. Our result is most interesting if the lower bound side is tight, then the number of edges that we queried is gonna be n to the power of 1 plus little o of 1 divided by p, which is very good. So some definitions before we dive into the result. We let opt to be the minimum vertex cover of G star, which is a random variable since G star is random. Remember that G star is the realized graph where we have the G as the stochastic graph that is given to us as the input. We let mu of a graph to be the size of the maximum matching of that graph. For any vertex V, we define CV to be the probability that that vertex V is in the optimal solution. And this means that the sum of CV over all the vertices is gonna be opt because of linearity of expectation. Similarly, for any edge E, we define CE to be the probability that this edge is covered by the optimal solution. It means that what's the probability that either U joins the optimal solution or V joins the optimal solution. Two more definitions, and then we go to the algorithm. Um, so we define graph hallucination. Let's suppose that H is a subgraph of G. We define the hallucination of H to be the subgraph H star, which contains an edge E uh, in H independently with probability PE. So you can say that H star uh, on the particular subgraph of H has the same distribution as the input on the subgraph H because both of them have each edge present with probability P. And then we define RS of T to be the largest number of induced edge disjoint matchings of size T in an n vertex graph. So we just drop the n in RS because we always have an n vertex graph. So what's the algorithm that we have for the finding the minimum vertex cover for G star? The algorithm to query to determine the query subgraph is very simple. We just set Q to be the subgraph of edges with CE less than a threshold 1 minus tau. And then we get the Q to get Q star. Recall from the beginning of the talk that I said if we provide Q, then it's enough to compute the approximation ratio because we had to cover all the edges in Q star and cover all the edges outside of Q. So we combine these graphs and then we take the minimum vertex cover and of that graph and we report that. But here, for the sake of analysis, because the analysis of this algorithm is very hard, we do a different algorithm that still gives us the valid vertex cover, but the benefit is that we can analyze its approximation ratio easier. So here we set the graph H to be G minus Q, and then we hallucinate H to get H star. Then we set P1 to be the minimum vertex cover of Q star union H star, and we define the graph R, which is short for remaining graph, as the H on um, the induced subgraph on H with the vertices V minus P1. And then we let P2 to be the minimum vertex cover of this remaining graph. And at the end, we report P1 union P2. So the first claim we're going to prove is that the output of the algorithm is a minimum vertex cover. This is really easy because P2 is the vertex cover on the graph that P1 doesn't cover. And then we can easily say that P1 union P2 is a valid vertex cover. The second claim is that the expected size of P1 from this algorithm is equal to size of the optimal solution, and the distribution of P1, like what's the probability that each vertex joins P1 is the same as the optimal solution. Why is this true? Let's look at how we build P1. We take the minimum vertex cover of Q star union H star. Q star union H star has the same distribution as G star. Why? Because this is because each edge is present in Q star with probability PE, and each edge is present in H star with probability PE, and they're all independent from each other. So then we get that Q star union H star has the same distribution as G star, and minimum vertex cover of G star is simply the distribution of opt. So P1 has the same distribution as opt, and the size of it is the same as expected value of the size of the optimal vertex cover. Then next lemma says that if the algorithm does not have an additive approximation of at most k in expectation, then expected size of the maximum matching of R is at least k over 2. So due to the previous claim where we said P1 has the same size as opt, whatever is the additive approximation ratio is due to P2. So this means that expected size of P2 is at least K. And in any graph, the maximum matching is at least half of the size of the minimum vertex cover. So the maximum matching in R is at least K over 2. So that concludes the proof. So let's dive into how we find the large RS graph in H. Um, The algorithm to find the large RS graph in H is also really simple. For T rounds, from 1 to T, we hallucinate G to get GI star. Then we let PI to the minimum vertex cover of GI star. So PI, you can say that it's from the same distribution as opt. Then we let Ri to be the subgraph of H, the induced subgraph of H on the vertices V minus pi. Uh, these are the vertices that are not covered by pi. Then we set mi to be the maximum matching of ri, and then we delete edges in mi present in at least one other rj with j not equal to I to get si's. And then we return the collection of S1 through ST. So just to recap, mm, at each step we get a graph Ri, which is based on a hallucination of G and a vertex cover of that graph. And all of these graphs Ri each have a maximum matching, which we call Mi. And from each Mi, we delete the edges that are present in another uh, Ri. We're gonna see why we do the deleting at the end because MIs are valid matchings, and we can say we might be able to say that collectively they make a large RS graph, but for them to be induced matchings, we need to do the deleting part. So our goal is to prove the collection of SIs from a large RS graph. If we take T to be very small, then we do not have enough induced matchings. And if we take T to be very large, then the size of SIs will be small due to edge deletions. So we have to tune T in a good way to get the bounds that we want. But we get to that later in the talk, to how to set T. So our first claim is that for any edge E and any graph Ri, the probability that E is present in Ri is less than tau. This is because E is in Ri only happens when E is in the graph H, which means that CE is gonna be greater than 1 minus tau because recall that we set Q to be the subgraph of edges that have CE less than 1 minus tau, and then the subgraph H, which was the complement of the query graph, which is gonna be C's that are greater than 1 minus tau. So if C is greater than 1 minus tau, then the probability that um, it is covered by pi is 1 minus tau. So with probability 1 minus tau, it's not even gonna be in the Ri because it's gonna be covered by a vertex in pi. So with probability tau, it's with probability at most tau, it's gonna be in the graph Ri. The next claim is that the matchings Si returned by algorithm 2 are induced matchings. This is because Ris are induced subgraphs. And to be more specific, let's suppose that we have two edges in S1 and an edge in S2, which makes S1 not an induced matching. Then because all of these four vertices are in S1 and R1 is an induced subgraph, this edge is also gonna be in R1. And so this edge will get deleted from S2 because it's present in R1. So it's crucial that we do the deleting to get induced matching. The next claim is that suppose we set t equal to 1 over 2 tau, then we have expected size of Si greater than k over 4. Recall that we had expected size of Mi greater than k over 2. Now we should argue that with edge deletions, Mi will lose at most k over 4 edges in expectation. Why is this true? Because uh, recall that from the previous claim we had that each edge is present in each Ri with probability at most tau. So when we set t to be 1 over 2 tau, um, If we multiply this by tau, 1 over 2 tau multiplied by tau, we get the probability of 1 over 2. So by union bound, we can show that any edge will be deleted from mi with probability at most half. So at least half of the edges will be in Si. So the size of Si will be at least k over 4. The next lemma says that by running the process above in algorithm 2, we can find RS and RT graph with t equal to 1 over 2 tau and r equal to k over 8. I'm just gonna say the proof idea here. The proof idea is that we break the matchings of size k over 4 in expectation to matchings of size exactly k over 8. I'm not gonna go into the details. So let's summarize our result for the additive approximation. Suppose that we set T to be RS of epsilon n over 8, which means that what's the maximum number of matchings of size epsilon n over 8 in uh, n vertex RS graph? So then we run algorithm 1 with tau equal to 1 over 3 t. This finds a vertex cover that has additive approximation of at most epsilon n to the optimal minimum vertex cover, and core is a subgraph of size Tn over p. So for the proof, recall this lemma that we had, that we can find RS and RT graphs with t equal to 1 over 2 tau and r equal to k over 8. Then if we set k to be epsilon n, we get t prime equal to 1.5 t induced matchings of size epsilon n over 8, which is a contradiction with the definition of RS function, because mm, the RS function gives us the maximum number of matchings with epsilon n over 8 size. So if we find 1.5 t induced matchings of size epsilon n over 8, then that's a contradiction. So I'm just going to briefly talk about how we get a multiplicative approximation. The idea is that we commit vertices with high CV to the final solution. CV was the probability that this edge is in the optimal solution. So if the probability that the vertex is in the optimal solution is very high, then just might as well include it in the final solution. So we commit vertices with CV greater than 1 minus alpha epsilon to P0. Now we need to cover the rest of the graph, which is G of V minus P0. Then we do the algorithm 1 on G V minus P0, and then we return P1 union P0 union P1 union P2. And then we prove that this gives us a multiplicative approximation. The ideas are very similar to the previous algorithm to get this approximation ratio, but due to the lack of time, I'm going to skip over this. So our conclusion is that we design a simple algorithm for finding 1 plus epsilon approximation vertex cover in the stochastic setting. The number of queries is dependent on the density of RS graphs, which is n times RSn. And of course, the open question is that is it possible to get 1 plus epsilon approximation using order of n over p queries? And thank you for listening. I'll please ask the questions if there's any questions.